Hi everyone and welcome to Byju's. In today's session, we are going to solve and discuss the JEE Mains 2020 paper that happened on the shift 1 of 7th of January. And before we move forward with solving each and every individual question, let's talk about the paper in a slight detail and the distribution of the questions. Now, if we talk about bucketing the questions in terms of physical, organic, and inorganic, I would say that physical, organic had a similar share. For example, physical had 7 questions, organic had 8 questions, and inorganic had the maximum share, that is, it had a total of 10 questions. And if we talk about the distribution of questions in terms of the grades over there, we had 12 questions in the 11th standard and 13 questions in the 12th standard. And now, let's talk about which all questions came from which particular chapters and their corresponding concepts. Alright, so starting with physical chemistry over there, we have the quantum number question from atomic structure. We have the Dalton's postulate question from mole concept. Remember the Gibbs free energy change question from thermodynamics? Right? Okay. From ionic, we had the pH question. From kinetics and nuclear, we had the SR90 decay question. From electrochemistry, we had the EMF question. And we had the positive deviation from Raoult's law, the vapor pressure question from solutions. Moving on to organic over here, we had the basicity PKB question from GOC. And remember that question which had the formation of Grignard's reagent, which had NaBH4, PBr3. We are clubbing that into organic compounds containing oxygen. And why so? Because it had basically alcohol over there, it ended up with a carboxylic acid, it started with an aldehyde. So we are clubbing all of those together into one bucket over here. If we talk about the epoxide question, we would attribute that to alcohol, phenols and ethers, and the methyl orange questions to amines. Because even though some might feel like that belonged to ionic equilibrium over there, it was more of an amines question, because without that knowledge, we would not have been able to solve it. Talking about the separation question, where we were separating the mixture of M-chlorophenol, M-chloroaniline and M-chlorobenzoic acid into 3 fractions, that would be some basic principles and techniques in organic chemistry. And another question where we were asked which of the following will not form the saytzeff product, that's obviously GOC. Then again, we had a disease matching question with the vitamins, disease, right, deficiency diseases, right, that is belonging to chemistry in everyday life. We had the chloramphenicol question, the number of chiral carbons from biomolecules. Now moving on to inorganic chemistry over here, we have the electron gain enthalpy question from periodic properties. We have the van der Waals interaction comparison and dipole moment comparison of the net molecule, right? For CCl4, for CH4, for CHCl3 over there from bonding as well. We have the oxides, superoxides and peroxides of potassium from S block. We have the hardness question from hydrogen. We have the wrought iron question from metallurgy. We have the reaction of Cl2 with hot and concentrated NaOH from P block, obviously group 17. We have the comparison of radius of silver, nickel, copper, gold and mercury from D block. And we had 2 questions from coordination compounds, the nickel carbonyl complex over there and obviously the IUPAC nomenclature. So that was the question-wide distribution with respect to the component chapters and the individual concepts that constituted them. Now let's move forward with solving the questions. Alright, so let's move forward with this question, right? What is this question saying? It's saying that the relative strength of the inter-ionic / intermolecular forces in the decreasing order is, right? Okay, further we have been provided these options over here. And if you look at the options, right, the elements in the options are essentially what? Ion-dipole interactions, right? Then dipole-dipole interactions and ion-ion interactions. And they sort of are getting jumbled around in options A, B, C and D, right? Okay, cool. Now, right away we know that the correct answer over here is going to be essentially what? Option C. That is the ion-ion interactions are going to be the, maximum of the maximum strength, followed by ion-dipole interactions, followed by dipole-dipole. That is essentially what? Option C over here. But just to clarify this a further bit over here, right? What is the type of force that is acting in between the species over here, right? It's obviously going to be what? Electrostatic force over here, right? And essentially the formula for that one, which we definitely know, is basically what? KQ and Q2 divided by R square, where R is essentially what? The distance between the two species we are considering, right? Okay, cool. Now, in the first option over here, right, what do we have in the first diagram over here? What do we have over here? We have a positive charge, we have a negative charge. They both have a unit charge on top of them of opposite signs over here, right? If we look at the second case over here, right, what we have done is we have considered the case of essentially what? Ion dipole interactions, right? So the only degradation that has happened over here is that if you look in this particular case on this end, you would realize that in the previous case we have a whole unity of negative charge, and in this case over here we are going to have del negative. That's going to be a slight negative value, which is going to be less than, you know what, in terms of magnitude, less than -1, right? Okay, cool. And coming over here to the third case, when we look over here, right, when we realize that if we compare this end over here and this end over here, what essentially has happened is that both the value of Q1 and Q2, if we start comparing the electrostatic forces of first, second, third, has basically, you know what, reduced essentially as compared to the first and second case. And that is why over here, right, that is going to have the least amount of, you know what, least strong forces over here, right? Okay, cool. Then again, you can see as basically, you know what, the forces are starting to decrease as we move from top to bottom over here in these three cases. These two entities over here are also moving away from each other, right? That's why the distance between them is increasing. And with that, this question is pretty much sorted. Not much to be done over here, right? Not much to be solved over here. This is pretty much very, very basic stuff of chemical bonding. And with that, we can, with certain confidence, we can say that the correct answer over here is essentially going to be option C. Alright, moving forward with this question, right? Let's see what does it have. Okay, so it's saying the oxidation number of potassium in K2O, K2O2 and KO2 is essentially basically what, right? Okay, further we have been provided with 4 options over here, and basically, you know what, they have different values of the oxidation state separated by commas over here, and we have to choose the right option. Now this question is not that difficult because we know what we are dealing with, right? We know we are dealing with essentially what? We are dealing with potassium oxide over here, then we are dealing with potassium peroxide over here, and then we are dealing with potassium superoxide over here, right? Okay. And when we study oxidation state for the first time, we know that when we are dealing with, you know what, S block elements, if we are talking about group 1, the oxidation state is always supposed to be taken as basically what, +1, and for group 2 over there as +2, right? Okay, cool. So in all of these compounds, right, in all 3 of them, essentially what's going to happen is that we are going to take the oxidation state of potassium equals to +1, right? And with that, this question is sorted because we know right away that these values, that is +1, +1, +1, is only provided in option C over here. So we are pretty sure about that. But at the same time, another question could have been asked about the oxidation state of oxygen over here. And how do we answer that? We basically know that if we are talking about this compound, right? If we are talking about this compound over here, what are we going to do? We are going to take the oxidation state of oxygen as X, right? Further, what we are going to do is we're going to take 2 bracket 1 over here for potassium, right? Plus we are going to do X for oxygen over here, and basically that tells us that X over here, that is the oxidation state of oxygen, is going to be -2, right? Okay. Now similarly, we can do a similar calculation for the second compound over here. Now what do we have? 2 bracket 1 for potassium and 2 bracket, basically let's call it Y over here for oxygen is basically this, and Y comes out to be -1 over here. That's why we called it potassium peroxide over here. And if we basically, you know what, talk about the third compound over here, KO2, which is called as potassium superoxide, what do we have over here? We have basically what, 1, right? Only no 2 over here because we have only 1 potassium. Then what do we have? We have 2 bracket Z for oxygen equal to 0, and Z comes out to be -half, which is basically what, wherever you have oxygen in -half oxidation state, you're dealing with a superoxide over there, right? Okay. So although this was not asked in the question, but to be honest, right, we are not very sure about the quality or the, you know what, the correctness of these questions because these are more or less memory based sourcing. So it could be possible that even though we have found out this question to be there in its exact format, right, from multiple sources, it could also be the case that the question actually asks the oxidation state of oxygen, and for that we have provided this alternate explanation, right? Had it asked about potassium only, then right away we know we are talking about option C being the correct option for this particular question. Alright, moving forward with this question, what do we have over here? It's saying at 35 degrees Celsius, the vapor pressure of CS2 is 512 millimeters of mercury, right? Okay, cool. Further, it's saying that of acetone is 344 millimeters of mercury. And now a solution of CS2 in acetone has been formed over here, and the total vapor pressure is coming out to be 600 millimeters of mercury, right? Okay. Now the question over here has provided us with a couple of statements, and now it is asking us to identify the false statements among the following, right? Okay, cool. So let's see about that. So what is the first statement saying? CS2 acetone are less attracted. Okay, second is saying heat must be absorbed over here. Raoult's law is not obeyed in the system. Okay, a mixture of these many mLs of CS2 and these many of acetone has formed. So the combined volume will be less than 200 ml. Okay, fine. So it's basically, talking about whether the solution will deviate, and if so, which direction it will deviate in, right? Okay. Now the point over here is, right, I have a diagram made up over here, and I want you to, just take a deep breath, right? Just take a deep breath, right? Okay, lie back in a chair over there and look at the diagram over here. Don't try to absorb all of it at once, right? Okay, cool. So we'll start with the labeling over here, right? So we have vapor pressure on the y-axis. We have mole fractions on the x-axis, but that labeling over here is a slightly, non-familiar one if you do not remember this particular section of the chapter, right? Okay, cool. Further, what has happened over here is, right, by the dotted lines, we have tried to plot the, ideality of the Raoult's law, right? When the mixture over there is basically, an ideal mixture over there, and it perfectly follows Raoult's law, and which is basically that the total pressure is essentially going to be equals to what? XA multiplied by P naught A, and basically what you add to it, you add XB multiplied by P naught B over there, and this is what you get. Now the point over here is, right, the dotted lines over here, right, they are following the Raoult's law perfectly over there, right? But the lines that we have drawn, the solid lines over there, they are not showing the, ideality over there. They are actually showing a positive deviation. And what do I mean by that? I'm trying to say that the actual total pressure is coming out to be actually more than this expression on the right, and that is what we have on our hands over here. Now, why does that happen? Now, the point over here is, right, if you have one particular system over here, right, that has a certain vapor pressure, right? Okay, cool. Now, you have another system. Now, what I want you to do is, I want you to combine these two systems into one system, right? Okay. Now, what's going to happen is, you're going to have molecules of A, let's say that is basically what CS2 over here, and you have molecules of B, let's call that acetone over here. Now, we are going to discuss in terms of A and B, but we are going to constantly, switch between acetone and CS2 as well, right? Okay. So the point is, you have A and B over here, but the point over here is, right, when you observe a positive deviation, essentially what happens is that, assume that I have A over here, right? Now, generally it is surrounded by a lot of A molecules, in its surrounding, right? Okay, cool. Now, when I mix B into it, or I mix A and B together, what's going to happen is that some of the surrounding molecules of this A, right, which were earlier pure A and only A, are now going to be some B molecules, right? Okay. Now, the point over here is that if the interaction or the intermolecular attraction between A and B molecules is not that strong, what's going to happen is that these molecules are going to be more tempted, or are going to have a higher tendency to escape their liquid form and enter the vapor form, which is going to, result in a higher vapor pressure, right? So that is what is happening over here. Since CS2 and acetone, right, do not have good intermolecular attraction if you compare them to their individual intermolecular attraction, as in CS2CH2 or acetone over there, right? On mixing over there, the net intermolecular attraction in the entire system over there essentially can be said to have reduced, right? Okay, that is why you have an increased vapor pressure, right? The PA value has also increased, the PB value has also increased, and definitely because of that, the P total value has also increased, right? Okay. Now, why have we drawn this diagram over here? Why have we not drawn the negative deviation, right? The reverse diagram over here, right? Because we know basically what, if you look at the right side of it, I have basically, labeled 512 millimeters over here, and on the left side, I have labeled 344 millimeters over here, right? Okay. Now, if you follow the dotted purple line, that is the ideality situation of P total, you would realize that this dotted purple line can never acquire a value that is more than 512, right? Okay, it can never acquire a value that is more than 512. That is the ideality over there. And even if there was a negative deviation, right, this dotted purple line would actually go down, right? So it would never be able to acquire a value that is more than 512 in any of the, mole fraction values or molar ratios you would have mixed them in. And because of that, what we are going to state over here is that since in the question over here, we have basically what? The total vapor pressure coming out more than the pure vapor pressure of CS2 over there, right? Okay, cool. Yeah, CS2 only, right? I forgot the values for a minute. Okay, so CS2 over there, we know that since the total vapor pressure is indeed coming out to be more than the pure vapor pressure of CS2 over there, this indeed a case of positive deviation and not a case of ideality or negative deviation. Right? Okay, cool. Now with that information, we can proceed forward, and what do we see over here? The first option over here is saying CS2 and acetone are less attracted to each other than themselves. That is indeed what we talked about, right? So this statement is correct, but the question is asking for the false statement, so this is not going to be a correct response, right? Okay, cool. Let's move on. Heat must be absorbed in order to produce the solution at 35 degrees Celsius. That is also indeed true, right? Why is that true? Think about it, right? So when bonds form in a proper bond formation, right? Go back to the basics, go back to the fundamentals, right? Chemical bonding. When bonds form, energy is released. When bonds are required to be broken down, energy is to be provided. Well, over here, I cannot say that chemical bonds are being formed or broken, but we can say that as an entire system, if you look at it, right, the total intermolecular forces over here are getting weakened, right? If they are getting weakened, they must have absorbed some energy in the process, and that is why we'll say that statement B over here is correct as well, right? Okay, cool. It's definitely not a correct response. Let's move on. Raoult's law is not obeyed by the system. That's been the crux of the whole discussion over here. Let's move on to D. Well, A, B, C are indeed correct statements, so D has to be wrong. So we already know what the correct answer is going to be. But for the sake of understanding, let's look at it, right? Okay, cool. A mixture of 100 ml CS2 and 100 ml acetone has a volume less than 200 ml. No, it's actually going to be more than 200 ml, and that is the exact reason what we talked about, that when A and B are mixed, the total, strength, the net strength of the intermolecular forces in the system is going to reduce, which is going to, expand the liquid system over there, or expand the volume over there by a bit, right? Okay, so what we can say is that delta V mixing over here, right, is essentially going to be more than 0, and with that, with 100% certainty, we can say that option D over here is indeed turning out to be the correct response for this particular question. Alright, moving forward with this question. This question over here is asking us that the atomic radius of silver is closest to nickel or copper or gold or mercury, right? Okay, cool. Now, although a lot of you people, right, might have, a good idea of which elements lie where in the periodic table, and some of you might even remember the correct order of different elements in different series, I've drawn this, very rough outline of the periodic table over here just to, put these elements over here in perspective and just, some sort of an anchor point, right? Okay, cool. So what do we have? We have nickel over here, we have copper over there. So what do we have? We have iron, cobalt, nickel, copper, zinc, right? So we have basically what? We have basically copper over here somewhere, right? Okay, cool. Then what do we have? We have nickel over here somewhere, right? Okay, cool. Apart from that, if we talk about silver or, okay, fine. So let's talk about gold and mercury first, right? So what do we have? We have basically what? Lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury, right? And that's the end of basically what? That's the end of 5D series over there, right? So gold, mercury is the end. So mercury is somewhere over here and gold is somewhere over here, right? Okay. And in a similar fashion, if we talk about the 4D series, right? Yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, right? So basically it's the second last element of the 4D series over there. So we have silver over here, right? Okay, cool. Now the point over here is, right, when we are trying to compare the radius of silver, right, with these elements, right, essentially what can we say is that if we talk about a particular group, right, so let's talk about this particular group over here, right, copper, silver and gold, right? So the normal expected order over here would be that copper should have the, you know what, smallest size, then we should have silver, then we should have gold. Why so? Because we generally think that basically down the group, since new shells are being added, so the size should increase, right? Okay, cool. But what is happening over here is, right, when we are trying to, you know what, go from silver and when we are finally, you know what, reaching cesium over here, right, when we have lanthanum over here, right, we do not reach gold directly, right? In between what happens is that we enter this atomic number 58 over here, right? We have basically what, cerium over here. From cerium we go till atomic number 71, lutetium over here, and then again we land on basically what, hafnium over here, atomic number 72, and then we basically, you know what, afterwards land on gold, reach gold essentially. Okay, so what has happened in between all of this journey is that essentially, you know what, because of the poor shielding of F electrons over there, since 14 electrons were added alongside 14 protons were also, you know what, increased kind of in the nuclear charge, right? Basically what we say is that because of the poor shielding of F electrons, the Z effective has considerably increased, right? So even though the expected order was that copper should be the smallest one, then we should have silver, then we should have gold, turns out that gold is not that big. Gold has actually shrunk down because the nucleus inside, right, is able to apply a considerable force on the outermost electron of gold over there, and so it's able to, you know what, kind of contract its electron collection, and the collective size of gold over there comes out to be, you know what, similar to the size of silver as well, right? And that is why for this question over there we'll say that the size of silver is closest to gold, and with that we can easily see why option C over here is turning out to be the correct response, right? Okay, cool. Now the point over here is, right, that if you look at copper and nickel, we can basically, you know what, remove them right away, and if you go look at the data over there, it turns out that mercury does indeed have a larger size, so that's not going to be one of our options as well. And with that we have basically, you know what, eliminated 3 of the options, and gold over here is turning out to be the exact correct response for this particular question. Alright, so let's move forward with this question, right? It's asking us the dipole moment order for CCl4, CHCl3, CH4, right? Okay. And the options are basically, you know what, given us some sort of a relationship between the dipole moments of these 3 compounds, right? Okay, cool. Now the point over here is, right, when we look at CCl4 and CH4, right away we know that their net dipole moment essentially is going to be 0, right? And that is what we have depicted over here. Why? Because they are regular geometries, right? And especially with regular geometries, all the terminal atoms are essentially the same in one particular compound, and because of that over here, right, their net dipole moment for the entire molecules for CCl4 and CH4 is essentially going to be 0, right? Okay. Now, as soon as we have that CCl4 and CH4 dipole moment is actually going to be 0, we know that right away over here in the options, right, the option with having the equality, that is option C, is going to be the correct one, right? Okay, cool. Now when we look at CHCl3 over here, right, in this diagram you can clearly see that essentially the net dipole moment is not going to be 0, right? It's going to essentially add up, and there will be a non-zero value, and because of that we'll say that the dipole moment of CHCl3 is going to be more than dipole moment of CH4, which is going to be equal to the dipole moment of CCl4, and with that, with perfect confidence, we know that option C over here is indeed going to be the correct option. Alright, so this question over here is saying that in comparison to the zeolite process, for the removal of permanent hardness, the synthetic resin method is essentially what, right? Further, we have been provided with 4 statements that could, continue the statement of the question, and they have been provided in 4 options, right? So let's select the correct one. Okay. So over here it's talking about, the synthetic organic resins method or the synthetic resins method over here is less efficient, more efficient, okay, as it can exchange only anions, only cations, okay, as the resins cannot be regenerated, okay. So C option is definitely incorrect over here because they can be regenerated, right? That is one of the benefits they have, right? Okay. So synthetic organic resin method over there, right? It is quite cheap. They can be regenerated again. So that's one of the positives, right? Okay. Along with that, even another property which makes them superior to the zeolite process is that essentially if you have the zeolite process, right, you're going to end up removing the ions of Ca2 plus and Mg2 plus over there from the hard water, and they're going to be replaced by Na plus, right? Okay. But if you're using the synthetic organic resins, right, what's going to happen is it's going to remove all types of ions from it, right? You have cation exchanges, you have anion exchanges as well. So basically it's more efficient and even superior to the zeolite process because it is able to remove the anions and cations, both of them, right? And that is why it is called as superior or efficient or better than the zeolite process. And with that, we know that the answer to this question over here is essentially going to be option D, which is saying more efficient as it can exchange both cations and anions. So let's mark the the options over here as option D, and it is time for us to move on. Alright, now this question over here has given us a couple of statements, and now it is asking us that which one of the following was not proposed by Dalton, right? Okay, cool. First of all, do not look at this question, right, from basically, as in this is a very simple question, this is not a difficult question. Why are they asking such questions like that? First of all, this question is a boon, right? Appreciate this question, right? Thank the examiner for setting up a paper which has questions like these. It's good. Second of all, if we talk about the options over here, option A over here is definitely correct, right? Dalton did say that yes, atoms are indivisible, right? And matter is basically, consisting of atoms over there. And so a statement over here, statement A definitely was proposed by Dalton, right? Okay. So A is not going to be the answer because the question is asking us which of the following statements was not proposed by Dalton. Okay. Further, moving on, B statement over there is saying that when gases combine or react in a chemical reaction, they do so in a simple ratio by volume, provided all the gases are maintained at the same temperature and pressure. Well, this is not Dalton's. This is more something that we study a bit later on in mole concept, and this is basically, called as the Gay-Lussac's law. This comes right before Avogadro's hypothesis, if you remember, right? So basically, this is not Dalton. So with that, we are dead sure that for this question over here, this particular statement, that is option B, is indeed going to be the answer. But just for sanity's sake over here, let's just go through option C and D as well, right? Okay. So now option C over here is saying chemical reactions involve reorganizations of atoms. Well, Dalton did not say that exactly, but he did say that, right? Basically, atoms of different elements or the same elements, in fact, might combine in, simple ratios to form compounds, right? What is that happening over there? right? Even when the reaction is happening, right, the atoms are conserved, right? So if the atoms are conserved and atoms are combining in simple ratios, their reorganization is essentially the only plausible thing that could be inferred from it that is going to happen, right? If the atoms cannot be destroyed, right, that is the primary thing, only the reorganization can happen, right? And if the fixed ratio is there, that is further indication of a chemical reaction, of a balanced chemical reaction. Okay, so statement C, while not directly proposed by the Dalton's postulate, is indeed, can be concluded from taking any of, any one or two of Dalton's postulates. Okay. Talking about option D over here, atoms are neither created or destroyed in a chemical reaction. That indeed is true as well, right? That is the whole principle on which we have, devised the entire laws that come forward and the entire balancing of chemical equations over there. And so we have gone through options A, B, C, and D. While this was a simple question over there, right? Do not look at this question in haste. This is a good question in terms of, good questions for me as a student if I look at it that way, right? Okay, so with that we can certainly say that why option B over here is indeed going to be the correct response. Alright, so in this question over here, we have been provided three compounds. We've been asked to compare their pKb values, and from the options we have to choose the correct order, right? Okay. Now there's nothing difficult in this question over here, right? But we'll start with 2 and 3, we'll come back to 1 later on, right? Okay. Then again, there's two types of mistakes that can happen in this particular question, right? The one is the obvious mistake that you mess up in finding out which one over there has the strongest basic nature over there, or which one over there has the lowest basic strength. That is the one type of mistake. There's another type of mistake which is more frustrating mistake, right? So that is basically, that is very simple but yet important over there. And why it's important over there is that essentially, look, for example, we have two compounds A and B, right? Okay. Now let's say their Kb values over there are, let's say 10 to the power minus 7 and 10 to the power minus 8 over there, right? Now we right away know over here, right, that the Kb value of A is going to be more than B. But if you find out the pKb values over here, those pKb values, right, that's basically what minus log of Kb, right? Okay. So basically this value over here is going to be what, 7, and this value over here is going to be 8. So 10 to the power minus 8, which actually was a lower Kb value, is ending up with a higher pKb value of 8, right? That's the point. So it's quite possible that you have determined everything correctly, all the strengths and everything, right? You have solved the question perfectly. But in the end, right? Basically, instead of Kb order, instead of pKb order, you're actually answering Kb order, right? And that is why I said or called it more of a frustrating mistake, right? Okay, so let's proceed with the question. We have basically what these three compounds over here. We'll start with 2 and 3. We'll come back to 1 later on, right? And believe me, it's not difficult that I'm leaving 1 for later. It's actually quite simple, right? Okay. So between 2 and 3 over there, right, if we talk about the hybridization of nitrogen, right, look at this nitrogen over here, right? Look at this nitrogen over here. This nitrogen is sp3 hybridized, right? And on top of that, it has 2 methyl groups, which are basically pushing electron density towards it. They are obviously Prusside groups, and that is why we have basically, 2 over there. Okay, we'll come back to 3. We'll go on to 3, then we'll come back to 2. Okay. So in 3 over there, right, the hybridization of nitrogen is sp2, right? That definitely reduces its attack or tendency of its attack on H plus over there, its H plus consuming tendency. And that is why if we compare 2 and 3 over there, we would obviously say that if we are talking about comparing the Kb values, we would obviously say that 2 has a higher Kb value as compared to 3, right? So this is definitely what we are going to say. Now, if we are talking about 1 over there, right, we will talk about 1, but in sort of a, non-traditional manner, right? So remember this compound over there, guanidine, right? Remember this guanidine? So guanidine essentially, is basically one of the most strongest organic bases, right? It's basically one of the most strongest organic bases and looks something like this. Wait a minute. Yeah. So it looks something like this over there, and this is what we have. Yes. Okay. Now we come back to the compound that we have over here, right? Just pay attention. If we come back to the compound over here and you realize, just notice the bonds are marking as white over here, right? Okay, look back at the structure of guanidine again. Okay, look back at it again, the white bonds in particular. What you suddenly realize is that if you replace the hydrogens, right? If you replace the hydrogens with these things over here, right? With these sp3 hybridized carbons over here, what's essentially going to happen is you're going to see the analogy between the two structures. Now guanidine, which I showed you over there, right, without these carbons over there, is already one of the most strongest organic bases, and now on those nitrogens over there, you have kind of added what? You've kind of added sp3 hybridized carbons, right, which are further going to, increase the electron density over there, further going to result in the increased basic strength over there, and thereby what do we have over here? We have that the Kb value of 1 is going to be quite more than 2, which is going to be more than 3, and this is what we have. But wait, this is not the final answer, right? We have to go back to our initial discussion of that frustrating mistake. So if this is the order of Kb, what should be the order of pKb, right? So basically we can say that 1 will be lowest, right, followed by 2, followed by 3 being the highest among the 3. And if you try to find this particular order in the options over there, we right away see that option B is indeed matching the answer that we have found, and that is why option B becomes the correct response for this particular question. Alright, now let's look at this question, right? We have a series of steps over here, right? And the final product, right? That is what we have to find out. That is what the options over there are listing, right? So let's get on with it. Okay, cool. So first of all, what do we have? We have NaBH4 over there, right? Okay, and we have basically what? In the substrate, we have a triple bond, and we have a carbonyl carbon over there, right? Now we know that the H minus from the NaBH4 will essentially be, used to reduce, but it will not be able to reduce the triple bond over there. It will actually, attack the carbon of the carbonyl carbon over there, and that is what we are going to get, right? So we get something like this over here. Okay, fine. Now the point is, the next reaction is not that new or difficult. We have basically, done this multiple times, right? There's an alcohol over there. We are making it react with PBr3. So essentially the most intuitive and the most natural thing is going to happen. The alcohol, the OH over there is going to be replaced by Br, and because of that, we get this over here, right? Okay, cool. Now the next set of steps over there are basically what? Mg ether over there, and we know what is going to form Grignard's reagent. Perfect. Okay, so this is what we get over here. Now the point over here is, right, when we make it react with CO2 in the next step, right, when we make it react with CO2, right, what's going to happen is that, as notified, right, the negative charge on the carbon over there is going to attack at the most electron deficient site of CO2. CO2 we know is an electrophile, but which particular site of it is deficient in electrons, right? Obviously it has to be carbon, and so the attack happens over there, and the pi electron density of one of the carbon oxygen bonds shifts to the oxygen, right? Okay. And as a result, you have this particular compound over here as your product over there, which on further reaction with H3O plus gives us COOH in place of COO minus, right? Okay, cool. All this while, right, those two pi bonds, right, they were not touched, right? That's the crux over here. Okay. Now, on looking at the options over there, what do we see, right? On looking at the options over here, we see directly that while B, C, D do not have the triple bond that we genuinely seek, A option there has it. Not only has it, it is also matching the product that we have obtained over here, right? And with that, with 100% surety, we can now say that option A indeed is the correct response for this particular question. Alright, so let's look at this question. What is this question saying? It's saying the number of orbitals associated with quantum numbers n equal to 5 and the spin quantum number equals to plus half. Although it doesn't make sense, to associate a quantum number, especially a spin quantum number, with an orbital, right? Rather they are associated with electrons. But let's see what this question is trying to say, right? Okay, cool. So first of all, what do we know? We know that over here, n essentially is equals to 5, right? Okay, that is certainly what we know. Now, based on the value of n, we can say that since L is equals to 0 to n minus 1, the values of L we are going to get are essentially going to be 0, 1, 2, 3, 4, right? Okay, cool. Now, since we know that 0 essentially, corresponds to S subshell, 1 corresponds to P, 2 corresponds to D, 3 corresponds to F, and 4 corresponds to D, we can write 4 corresponds to G. On basis of all of that, we can write that we are essentially talking about all of these subshells, right? Okay. Now, if we do a little bit of conversation regarding, how many orbitals are present in each of these subshells, we can right away see that 5s is going to have basically what? 1 orbital, 5p is going to have 3, 5d is going to have 5, 5f is going to have 7, and 5g is going to have essentially what? 9, right? Okay. Now, even if you did not remember that how many orbitals are going to be there in 5G, you can use the magnetic quantum number to find that number out, right? Okay. And the question is just that over here we can directly say that yes, if we have to basically find out the total number of orbitals, we just have to sum all of these numbers, that is 1 plus 3 plus 5 plus 7 plus 9, and that number over here comes out to be essentially what? 25. Right? Okay, cool. And with that, we have the answer to this question. But at the same time, even if the question had asked the maximum possible number of electrons associated with quantum numbers n equal to 5 and spin quantum number plus half, the value of the answer over here would still be equals to 25, because each of these orbitals can have only one electron that can have the quantum number of spin equals to plus half. Right? With that, we know that the answer to this question over here is essentially going to be equals to what? 25. Alright, now this question over here is quite simple, right? We kind of have been obsessed with the entire metallurgy of iron, so this question, should not be a surprise. This question actually, should be a sign of joy, because this is very basic information, and I hope a lot of you guys, ended up getting this question correct over here, right? Okay. So while this question is asking us the purest form of commercial iron, right away we know that the answer over here is actually going to be what? Wrought iron, right? Wrought iron actually has, the percentage of purity of iron somewhere around 99%, right? While the lowest of the three provided over here is obviously pig iron, which has somewhere around 91 to 95% or 94%, right? Cast iron obviously is in between the two, but most definitely wrought iron is the purest form out of these three provided, right? And indeed, the most purest form of commercial iron, it has basically, carbon impurity somewhere around 0.08%, and in some cases even much lesser than that, right? So that is the purity standards of wrought iron, and with that right away we know that the answer for this question over here is indeed going to be option B. Alright, now this question is saying that the theory, right, from the given options obviously, that can completely or properly explain the nature of bonding in NiCO4 over here is essentially what, right? Okay, cool. Now the first point over here is, right, the most obvious answer that we rush towards is obviously CFT, right? Okay. But keep in mind that CFT does not tell us about the bond energies, bond lengths, the bond orders, or anything of the sorts, right? It does tell us about the shapes, yes indeed, but nothing of the sorts about bond attributes, right? Okay, cool. So definitely it's not CFT. And one more thing is that essentially, right, when we are talking about nickel over there, for example, or essentially any particular metal where such phenomena happen, what happens over there is that because of the presence of too many electrons in nickel, right, and further there's coordination from the carbonyl groups over there, there's presence of synergic bonding. Now what happens over there is that what we have observed is that because of this excess of electrons, right, there's actually kind of a back bond from the metal to the ligand. And that back bond, right, that back bond actually has involvement of the anti-bonding orbitals of the ligands, because of which the bond order of the carbonyl group over there decreases and the bond order of the nickel carbonyl bond over there increases, and that particular aspect of it explains the bond energies, the bond lengths, the bond order, obviously all of which are interrelated. And with that, all of these we can explain with the help of MOT, and because of that particular reason, this particular question is going to have the answer as not CFT, but rather MOT, which is actually what labeled as option C over here. Alright, so this question is asking us for the IUPAC name of this particular complex, right? So we have been provided a couple of names in the options, and there's this D option, none of these, right? So let's look at it. So first of all, what do we have over here? Let's draw that out first, right? So what do we have? We have PT, okay. Then what do we have? We have NH3 over there, and do we have one of it or twice of it? Okay, yeah, we have twice of it, okay. Then what do we have? We have chlorine over here, right? The name of it basically would be chloro over here. And after that, what do we have? We have methylamine over here. Okay, so let's plot that out over here as well, right? Okay, cool. Now over here, what do we have? We have Cl outside the complex ion over here, and which tells us that the complex ion over here is essentially going to be a positively charged complex, right? Okay, cool. Further, what more we can do over here is that we can say that since this entire thing over here is charged with +1, right, we can further say that if the oxidation state of platinum is taken as X, we can take 2 bracket 0 for NH3, we can take 1 bracket -1 for chlorine over there, and then again we can take 1 bracket 0 for methylamine over there, right? Okay, and this should equals to basically what? +1 over here, and that should basically, you know what, lead us to the oxidation state of platinum over here. Now, what do we get over here? Think about it, right? So basically, if you look at it, the value of X is coming out to be +2 over here, and that is going to be the oxidation state of platinum. Now the point over here is, right, when the metal ion over there is essentially the part of a positively charged complex, right, we just write its name plain out just like that, right? So what are we going to have over here? We're going to have platinum, right? We are going to have platinum over here, right? Okay, and we are going to write bracket 2 in Roman numbers over here, and after that we should have chloride. Why should we have chloride? We should have chloride to account for this one here, right? Okay, cool. Now, if we talk about everything that's going to come before platinum, what do we have? We have the groups over here as basically what? Amine over here, right? Okay, so basically this is what we have. Then again, what do we have? What else do we have? We have chloro, and apart from that, what do we have over here? We have methylamine over here, right? So this is what we have. And since, right, what do we have? We have twice of amine over here. We are not going to use the bis prefix because this is a monodentate ligand over here. We are actually going to use diamine over here, and that is going to be the primary name over here, right? And why is that going to be the primary? Because obviously amine alphabetically, you know what, gets the preference. So we have that over here, followed by what should be over here, what should be after that. So think about it, right? After iamine over here, what should we have? We should have chloro, right? We should have chloro over here, and after that what else we should have over here? We should have basically what? Methylamine over here, right? So basically this is what we get, methylamine, right? So we have basically what? Diamine, chloro, methylamine, platinum 2, chloride as the IUPAC nomenclature. And if we look at the options over here, right away we can see that option A over here is turning out to be the correct answer. Alright, so now this question over here has provided us with propylene oxide, and the reagent has been provided as HBr, that too in excess, right? Okay, cool. Further over here in the options, right, the product has been provided and we have to choose the correct option with respect to the product. So I guess we'll have to, think about and see how this reaction is going to proceed. So let's start with the basic fundamental propylene oxide over here, right? Okay, cool. So this is what we have, right? This is what we have over here. Now what is happening is that the H plus of HBr, right, its reaction is going to happen, right? So the lone pair of oxygen over here, they are going to attack on the H plus, and we have the protonation of the oxygen over here, which basically, lands up to a product over here, something like this. Now this obviously is not the final product, right? This is only a step in the entire process. Okay. Moving on further, right, we did use H plus in our mechanism, right? So the left out Br minus, now that is going to proceed and attack via the SN2 mechanism, that is the less hindered side over here, and we are going to end up with something like this. But wait, this is not the final product. What is left is, looking back to the question, you'll realize that the question has provided us that over here we have taken HBr in excess. And what that is going to do is that excess of HBr is further going to, do its actions over here, and this OH, right, this OH, wait a minute, yeah, this OH is going to be further replaced, and we are going to get a compound like this over here, right? So we get basically what the OH got replaced by Br, and we got something like this. And coming back to the options over here, what do we see? We see right away that the answer that we have over here is directly matching with option A provided in the question, and now with 100% surety we can say that option A is indeed the correct response for this particular question. Alright, so this question over here has provided us a reaction over there, and further it's saying that the product X over there will basically, will be satisfying which of the following parameters provided in options A, B, C, and D, right? Okay, cool. So let's see about that. So what do we have over here? We have dimethyl aniline over here, okay. And what do we have over here? We have basically what? We have a diazosol, and the ring over there also has the sulfonic component, but that's okay, right? Okay, cool. So when we talk about this part over here, right? So let's actually proceed with the question. Let's see what do we have. Let's write it down all for once. We have dimethyl aniline over here, right? So this is what we have over here. Okay, cool, fine. And along with that, what do we have? We have something like this, right? Okay, what did we have at the bottom? We had SO3Na over here, right? You can further go forward and write something like this, minus and plus over there, right? It's perfectly fine. And over there, basically, what do you have? You have a diazonium, right? Okay, and you have chloride over there, right? Okay, cool. Now the point over here is, right, we know that the diazo part of the compound over here is essentially going to be what? An electrophile. And so when it attacks the compound 1 over here, it's going to look for the sites that are electron rich, right? Okay. Now when you consider the lone pair of these nitrogen over here, and when you consider them in being conjugation with the pi electron density of the ring over there, you realize that for this ring over here, the ortho and the para sites, are also going to be electron rich, as you might have guessed already. But because of these bulky groups over here, the ortho site is not going to be accessible, and so the diazo attack over here in the compound 1 is actually going to be at the para position, right? And as a result, the compound that is going to be formed is going to look something like this, right? So let's look at it over here. What do we have? We have something like this, right? So wait a second, yeah, okay. So we have something like this over here. Okay, over here, what do we have? We have basically what? This. Okay, and over here, what do we have? We have this over here as well, right? Okay, cool. So this is what we have, and this is what we have. Yeah, okay, fine. And then what happens is the attack on para position happens, and basically what do we get after that? We get something like this over here. And I'm not getting into the exact mechanisms, right, and all the different minute steps. I'm just, briefing on the entire process, and this is what we get, and this is our beloved, much more frequent than we expected to methyl orange, right? Okay. And as soon as we have deduced that we are talking about methyl orange over here, and we go through the options and the questions over here, you can clearly see that in option A, right, or option B or option C, if you compare them, option D stands out all of them, because we know right away that yes, indeed, methyl orange is used in acid-base titrations as indicators, and with that, with 100% confidence, we can say that the correct answer for this question over here is indeed going to be option D. Alright, now this question is a match the following, right? This is a matrix match. We have been provided with two lists over here. List 1 contains certain vitamins. List 2 contains certain diseases which occur on the deficiency of these vitamins. Now, obviously, these are not correctly matched, right? So that is what the question is. And if you look at the question, look at the options over here, that is exactly what has been provided in the options. Okay, so now let's start with this question. What do we have over here, right? So we have our list 1 over here, right? This is basically this is one of the list 1, right? And similarly, we have these over here, okay? And this is what we get, okay? Now, the point over here is, right, when we talk about riboflavin over here, we are essentially talking about vitamin B2 over there, and what that causes is basically it causes chelosis, right? Okay, cool. So it basically causes chelosis over there, and this is what we have. So basically that's what we know so far. Okay, fine. Further, another simple thing, right? Vitamin C, right? Vitamin C, which is a simple thing to recall essentially, right? Which we recall right away, is that this one over here causes scurvy, right? Okay, so this is what we have. Now, in a similar fashion, if we talk about vitamin B6 over here, or basically, pyridoxine over here, that basically causes convulsions, right? So this is what we have over here. And in a similar fashion, the only one that is left over here, that is thiamine over here. If we talk about that one over here, that one basically, causes beriberi, right? So this is what we have over here, and this should be the correct match. Now let's see about that, right? So beriberi, as I recall, but let's get back to the question over here. Okay, so what do I see? I see P over here, right? Okay, so this one over here is turning out to be P. Okay, so this is what we have. Then chelosis over there is turning out to be what? That is basically, turning out to be R. Okay, this is what we have. Scurvy over there is basically Q, right? Okay, and conversions is R. Okay, scurvy over there is essentially Q, right? Okay, and convergence is not R, sorry, S, right? Okay, and this is what we have. And now if we basically, wrote it down, the correct sequence is essentially coming out to be R, P, Q, and S. And if we go back to the options and realize which one over there is correct or not, we realize that R, P, Q, S is directly provided in option B over there, which makes us 100% certain over there that we can go forward by taking this question, and thereon we can conclude this question and move on. Alright, so let's look at this question. It's saying, given that the standard electrode potentials of Cu2 plus going to Cu is equals to 0.34, okay, and the standard electrode potential values for Cu plus going to Cu is 0.522 volts, right? The standard electrode potential values for Cu2 plus going to Cu plus has been asked. Okay, further we have been provided with these 4 options over here. So let's see about that, right? So, okay. What do we have over here? Let's write it down again. We have E naught, okay, Cu2 plus going to Cu over here, and the value has been provided as 0.34. Okay, fine. Okay. Then again, what do we have over here? Apart from that, we have E naught Cu plus going to Cu over here, and the value has been provided as essentially what? 0.522, right? Okay, cool. And what has been asked? It's been asking us about the E naught value for going from Cu2 plus to Cu plus. right? Okay, cool. Now, right away we can see, right, if we want to construct this third reaction over here from the above two, what do we have to do? We are basically, you know what, we are basically going to take this one over here as it is, right? And we are going to, in terms of reaction, I'm not talking about the values, right? And in terms of reaction, we are going to flip the second reaction and then combine the two, because that will cancel out the Cu and that will land Cu2 plus and Cu plus in the right positions with respect to the reaction that we want to generate, right? Okay, cool. Now the point over here is, right, whenever some question asks you about the E0 values or E values of a particular half cell, and it provides you 1 or 2 or 3 or 4 or many other half cell electrode potential values, right, you don't just add them up together according to the reactions, right? In that case over there, what you do is you multiply the number of moles of electrons in that particular individual reaction and then sum all of them, right? So let me illustrate my point over here. What I'm trying to say is that when we basically, you know what, combine the reaction 1 and 2, what we experience in terms of the equation of electrode potentials is not exactly the same as in when we have the first reaction value over here 0.34, we actually multiply it by 2. Why? Because the first reaction over there will involve the transaction of 2 moles of electrons. Maybe not even, you know what, direct transaction. Rather, since they are half cells, actually we can say that over here it will involve absorption of 2 moles of electrons per mole of Cu2 plus, right? Okay. Along with that, what are we going to have? First of all, we're going to have a -1, right? Why is that? Why are we going to have that? Because we are flipping the second reaction, and after that we are going to have 0.522 over there, and we are going to multiply it with 1, because Cu plus, 1 mole of Cu plus will absorb 1 mole of electrons and become Cu, right? For that very reason. Now the point over here is, right, what do we have to do? We have to calculate it. So the value comes out to be 0.68 minus, what do we have? Minus 0.522, right? Okay. Now you can calculate this value over here, or you can look at the options and decide which particular value out of these options is actually, you know what, turning out to be quite close to the answer that we have. Now obviously it's going to be a positive value, so we know right away option B and D are out of the race, and choosing between 0.158 and 0.182, we directly know that this value is going to be quite close to 0.158, and with that we can confidently say that why for this particular question over here, option A is indeed turning out to be the correct response. Alright, now this question is stated as that a solution of metachloroaniline, right? Okay, cool. So we have NH2, we have chlorine, fine, perfect. Then basically what do we have? We have metachlorophenol, OHCl, okay, perfect. And metachlorobenzoic acid, so CaOH, and then again Cl, okay, cool, at the meta position, fine. And ethyl acetate, so yeah, ignore that, cool. Initially was extracted initially with a saturated solution of NaHCO3 to give fraction A, okay, fine. And the leftover organic phase, which is basically, you know what, we had 3 compounds, right? We basically extracted one of them, and remaining 2 over there, right, were further treated and extracted with the help of dilute NaOH, and that gave fraction B. Okay, fine. The final organic layer was labeled as fraction C. Fraction A, B, and C contain respectively 4, right? Okay, cool. So now the point is, the question is not so difficult, right? Why? Because we have NaHCO3, right? And we know that out of the 3 compounds given initially, right, only benzoic acid over there is going to react with it, right? And further, what you have done is that essentially on benzoic acid, right, you have substituted a chlorine at the meta position, which has further increased its acidic strength over there, and that is why it will readily react with NaHCO3 and not so much with basically what? Metachloroaniline or metachlorophenol over there, right? Okay, so right away we know that to basically, you know what, that A, fraction A over there, that's going to be, you know what, utilized to extract basically what, metachlorobenzoic acid over there. So there we have it. Okay, cool. Further, when we talk about the leftover, right? So leftover contain the first two compounds, that is metachloroaniline and metachlorophenol. And now what are we doing? We are extracting them with the help of dilute NaOH, right? And that is giving us a fraction B. And then again, we right away know that if basically we had dilute NaOH and that was supposed to react with either of the two compounds, it would obviously be reacting with metachlorophenol and not metachloroaniline. Further, the chloro substitution in a similar fashion has further increased the acidic strength of basically what? Phenol over there. Okay, fine. And so we know basically, right? Basically, fraction B is essentially what? Metachlorophenol. And the final organic layers fraction C is going to be metachloroaniline. And there we have our answer, right? So what should we have over here? We should have the first one as metachlorobenzoic acid. We should have the second one over there as metachlorophenol. And we should have the third one over there as metachloroaniline. And if you look at the options over here, we find those options, those exact order, right, of the compounds in only option A, and with 100% certainty we can now say that option A over here is indeed going to be the correct response for this particular question. Alright, now this question is asking us to, look at all of these options, right? And the values over there are electron gain enthalpies. That's why you have the negative values over there, right? Okay. It's asking us to choose the option which has the right sequence in terms of, as has been provided in the question. That is, first should be fluorine, then chlorine, then bromine, then iodine, right? So, and in that manner, we have to answer this question. Now we know that when we talk about electron gain enthalpies, right, we talk about this in the very beginning as well, that is periodic properties, that basically when you're dealing with fluorine and chlorine specifically, right, you can also do the same argument that we're going to do for oxygen, sulfur as well. But more importantly, in case of fluorine and chlorine, right, what happens is that because fluorine belongs to the second period, right, fluorine belongs to the second period, right, it has a very, very small size, right, okay, cool. And because of the small size, what it has is that the electron density, right, the electron cloud around its nucleus is quite dense, right? Now, how that matters is that if normally someone asks me, like, what do you expect the electron gain enthalpy order of halogens to be? I would say that top to bottom, it should actually what? Decrease, right? That is what I would answer. But the actual order turns out to be, slightly anomalous, slightly not as expected. And the difference over there is that because of the small size of fluorine, because of the high electron cloud density over there, what happens is that the incoming electron, right, which is supposed to be accepted, faces some repulsions, right? Okay, so it faces some repulsions, and because of that, what happens is that what you expect, when you expect this much energy to be released, right, the net energy released is actually not that much because of that repulsion, right? Okay, cool. So what happens is, turns out that basically what happens, what did we discuss? That the topmost will have the highest electron gain enthalpy, right, in terms of the energy released, right? So we're actually looking here in terms of magnitude, right? Just for the consideration, ignore the signs in your head, just look at the magnitudes, right? So what are we saying? We are saying that the top to bottom, right? So fluorine expectedly should have the highest one, then there should be chlorine, then there should be bromine, then there should be iodine, right? Now what is happening was that here is chlorine, here is fluorine over here. Now fluorine has an actual value lower than expected, right? And turns out the experimental value turns out to be, less in total amount. That is what I mean is, ignore the sign for a minute, right? Less in total amount than chlorine, right? So now it turns out to be that the new order, the actual order, the experimental order or the observed order is chlorine has the maximum energy released, followed by fluorine, followed by bromine, followed by iodine, and this is what we have. Now, looking at the options over there, we directly see when basically, right, the highest value of all of these values is essentially what? That's basically what? 348, right? Minus 348 is the electron gain enthalpy, or we can say that 348 kilojoule per mole is being released, right? Both mean the same thing, minus 348 or basically 348 kilojoule being released per mole. Now when we see these values over here, we directly recognize that in option C over there, the highest value is placed on the second position, and in no other option 348 is at the second position, right? Okay, cool. So right away we know that option C is going to be answer, but let's just verify it, right? So what did we discuss? It's going to be chlorine max followed by fluorine followed by bromine, right? So fluorine should be more than bromine as well in terms of the magnitude. And right away we see that it has basically what, minus 333 as the value, followed by minus 324 for bromine, and followed by minus 295 for iodine over there, which means that for this particular question over here, option C indeed is going to be the correct response. Alright, so now in this question, right, we have been provided with 4 options, right? Okay, cool. 4 substrates, 4 reagents over there. So different conditions for each options, and we have to tick the options, the one in which, right, the reaction will not give us saytzeff product, right? Okay, cool. So this is what we have to do. So let's start sequentially. Let's start with the first one over here, right? So what do we have over here? Let's see. Okay. So we start with, you know what, just the basic compound that we have been provided. Now we know that basically, you know what we are dealing with is essentially equals to what, concentrated H2SO4, right? Okay, cool. So first of all, what's going to happen is that this is going to lead to formation of a carbocation, right? Okay, cool. Now if shifting is possible, once the carbocation has formed, it will happen, and over here we have basically what, 1,2-methyl shift, and because of that we end up with this thing over here. Okay. Now, the point over here is, right, what is left in this particular option over here? Only one last thing, right? We have minus H plus over here, and we get our final product. Okay. Now, as you can see over here, this is definitely basically what, a more substituted alkene over here, a saytzeff product. So this option is not going to be one of our correct responses for the question, right? So let's move on. Now, what do we have in the second option, right? So let's look at the question once. So what do we have in the question? Okay, so we have something like this. Okay, so now we have this compound over here. Now this one is not that difficult, right? We have been dealing with these questions like again and again, right? This is alcoholic KOH, this is normal base, right? What's going to happen, right? This over here and this over here, right? They are going to get removed, and basically we are going to end up with this as our product, which then again is a saytzeff product. So then again, this is not going to be one of our answers, right? Okay, cool. So let's move on. Now, C option, right? So we have basically, you know what, the same compound that we have in option B. Now, what do we have over here? We have basically what, this over here, right? So basically, this is what we have. Now, the point over here is, right, whether you basically, you know, remember that this is TBOK, right? Okay, so the point is whether you remember the name of it or you do not, doesn't really matter, right? It actually matters whether you can recognize that there are 3 bulky methyl groups attached to this carbon, right? Okay, so that is the most important conversation over here. And why that is important is that even though we might want to proceed like we proceeded in the previous option, it's not going to be feasible, because once we remove this, along with that we cannot remove this one over here, right? Because of the bulkiness of the 3 methyl groups over here, right? And because of that, what we'll have to do is we'll have to end up with, you know, 1 hydrogen of this CH3, which will lead to basically this product over here, right? Now definitely this is not a saytzeff product, right? This is a Hoffman product over here. So yes, option C over here does turn out to be, you know what, does look like it is going to turn out as a correct answer, but let's not hurry just now. Let's look at option D as well, right? Okay. So now this is what we have. We have aldol, right? And this is basically what, this is simply just the condensation of this aldol over here. And this is what we get over here, right? Okay, there's nothing fancy in this, right? This is what we get. And now as you can see, then again, right, what is this? This is then again what, a saytzeff product. So basically we have gone through option A, option B, option C and option D, and we have realized that only option C over here has a particular reaction in which we are getting a Hoffman product and not the saytzeff product, which means the answer to this question over here is essentially going to be option C. Alright, so let's look at this question, right? It's saying that two solutions, A and B, each of 100 liters, was made by dissolving 4 grams of NaOH, okay, and 9.8 grams of H2SO4 in water, respectively. Okay. Further, the question is saying, if basically, we prepared another solution by mixing 40 liters of solution A and 10 liters of solution B, then what would be the pH of that solution, right? Okay, cool. So let's consider this, right? We have the solution A over here, solution B over there, right? We have 100 liters of each of them. Now the point is, if we wanted to find out the number of moles of NaOH in solution A, that would be essentially equals to what? Given weight divided by molar weight over there, that is 4 by 40, that is equaling 0.1, right? Okay, so this is what we have over here. Now, in a similar fashion, if we wanted to calculate the number of moles of H2SO4, that will be equals to 9.8 divided by 98, then again equals to 0.1, right? Okay. The point over here is, right, we can say that the number of moles of NaOH essentially are equals to the number of moles of OH minus, but we cannot say the same for H2SO4 and H plus, right? The number of moles of H plus actually will be double the number of moles of H2SO4, and so we get this value of 0.1 multiplied by 2, 0.2, right? Okay, cool. Further, what do we have over here? We say that molarity of NaOH, right, can also be called as molarity of OH minus. That will be equals to, right, what? The number of moles divided by the volume, that is 0.1 divided by 100. And in a similar fashion, if you look at the middle bottom of the screen, you'll realize that molarity of H plus can also be said as its moles, the number of moles of H plus, that is 0.2 divided by 100 liters, right? So this is the values we get. Now the question is saying that essentially what are we doing? We are combining 40 liters of solution A, the solution which contained NaOH, and along with that we are combining 10 liters of solution B which contains H2SO4, right? Okay, cool. Now the point over here is, right, if we basically, wanted to find out the number of moles of OH minus over here, what would that be equals to? That will be essentially equals to volume multiplied by the molarity, that is basically equals to this value over here, right? Okay. And similarly, if we wanted to find out the number of moles of H plus over here, that will essentially be equals to 10 multiplied by 0.2 divided by 100, right? That was the molarity of H plus ions, right? Let's get back. Yeah, this is the value. Okay, cool. So what is this value coming out to be equals to? Let's not, calculate it completely. This is what we can say. Further, this is another thing we can say. We have 4 by 100 and 2 by 100 over here. And we can easily see that when these two things over here will neutralize, right, the remaining moles, right, basically will only be for OH minus, that is NOH minus. Remaining over here will essentially equal what? This will be equals to 2 divided by 100, right? Okay. Now if we wanted to find out, what pH, we basically have some OH minus remaining. So basically we will be calculating the concentration of OH minus, or in other words, we can say the molarity of OH minus, which will essentially be equals to what? 2 divided by 100 whole divided by the total volume. Now what will be the total volume? That will essentially be equals to what? 40 liters of A which were added and 10 liters of B which were added. So essentially that will be equals to what? 50 liters over here, and we get something like this. Further, what we can do is we can multiply 2 in the numerator as well as the denominator, and what do we get over here as a result? We get 4 divided by 10 to the power 4 over here, right? Okay, cool. So this is equals to what? 4 into 10 to the power minus 4, right? Okay. And if I want to calculate the POH over here, that essentially will be equals to what? That will be equals to what? Minus log of this value. So the 10 to the power minus 4 will essentially become equals to 4. And regarding this 4 over here, right? So it might be a bit confusing. 4 into 10 to the power minus 4. So the 10 to the power minus 4 will come out as 4, right? We are taking minus log of it. And the 4 over there, right, will actually be written as like in this particular format, right? So this is basically equals to what? This is basically 4 minus 2 log 2, or we can also say this is equals to 4 minus 2 bracket 0.3 approximately, right? Okay. Now if we have the value of POH over here, we can easily calculate the value of pH over there. That will essentially be equals to what? 14 minus the POH value, that is equals to what? 14 minus 4, that is 10, plus 0.6, that is 10.6, which essentially is the answer for this particular question. Alright, so let's move forward with this question, right? It's given us a situation, and over here, strontium 90 is getting absorbed in a human body, as the question is stating. Further, the question has already provided us the half-life of strontium 90 over here, right? And a certain amount of this strontium 90 over here got absorbed, right? Okay, cool. In place of calcium, okay, but that's, not important over here. Cool. Now the question is saying that how many years it would take for the initial amount of strontium 90 to basically, get reduced by 90%, right? So the most crucial piece of information in this question is that it gets reduced by 90%, not to 90%, right? That makes all the difference. And the initial amount, to be honest, is not even important, not even required, because to be honest, when we write the equation for first order over here, what do we know? We basically, can call it something like this over here, right? And inside the natural log over here, what do we have? We have the initial amount and divided by, we have the amount at time t. So since we are taking a ratio inside the natural log, it doesn't really matter about the absolute values, it's more about the relative values, and that the question has provided, right? And what is the question provided? The question has provided over here that the AT value essentially, right, it's going to be equals to 0.1 multiplied by A naught, that is 10% of the initial value, because it got reduced by 90%, right? Okay, cool. Further, the question has already told us the T half value, which is basically equals to 6.93 years over here. But at the same time, we also know that T half essentially is equals to ln2 divided by K over here, and that is what we are going to utilize, right? Okay. So what do we have to find? We have to find the T over here. We'll write this value over here as something like this, and we have ln of 10 over here, right? Okay, cool. Now what we can do over here is we can substitute the value of K over here, right? And what we can say is that 1 by K essentially is equals to T half divided by ln2, right? Okay. And over here we are going to convert the natural log into log to the base 10, which is basically going to be equals to 2.303 multiplied by log to the base 10 of 10, which is basically, going to be equals to 1, right? So this is what we have. Now the point is, then again, right, we also know that ln2 essentially is equals to 0.693, and over here T half has been provided as 6.93. So we can further cancel these two brown values over here, and they will turn out to be equals to 10 over here, and we have it getting multiplied with 2.303. That is the answer over here. That is the time, that is the number of years it would take to get reduced by 90%, is coming out as 23.03 years, which essentially becomes the answer for this particular question. Alright, so this question is asking us that if chlorine reacts with hot and concentrated NaOH and produces compounds X and Y, and in that compound X gives a white precipitate with AgNO3 solution, the average bond order between the chlorine and oxygen atoms in Y essentially is equals to what, right? Okay. Now over here, this is quite a common reaction, right? Cl2 reacts with NaOH. But then again, we remember two such reactions, right? Because over here in this reaction, right, the condition of the NaOH makes all the difference, right? So if you have hot and concentrated, or if you have, dilute and cold over there, that makes all the difference. And the products, all the products essentially in both the conditions are not the same. So in this condition over here, what do we get? We get NaCl over here, and along with that we get basically NaClO3, and along with that we get H2O. Now the point over here is, right, either this could be X and this could be Y, or this could be Y and this could be X, but that is why the second statement of the question has been provided, that compound X gives a white precipitate with AgNO3 solution, right? Okay. So if compound X over there gives a white precipitate with AgNO3 solution, compound X has to be NaCl, right? So basically compound X has to be NaCl, because NaCl will react with AgNO3 and will form a white precipitate of AgCl. And if basically NaCl is equals to or equivalent to X over here or labeled as X over here, we right away know that when the question is talking about Y, it is actually talking about NaClO3. Now, point is, if we want to find out the bond order between chlorine and oxygen atoms in NaClO3, we need to consider the structure of ClO3 minus. Now what is going to happen is Cl has 7 valence electrons of its own before the bonding. So how do we proceed with this? I'm not doing a complete proper structure of ClO3 minus. I'm just doing a Lewis structure over here because that is all we need. We don't need the bond angles and everything. We are only concerned with the bond order over here. And basically if you count the number of electrons chlorine contributed to the bonding over here, you can right away see that 2 electrons over here should be there, which should not be a part of the bonding. They should be non-bonding electrons. That is basically they will be lone pairs. Now if we take a look at the arrangement of chlorine and oxygen atoms over here, we see that in one bond they have a bond order of 2, in another they have the same bond, that is 2, and the third one they have a bond order of 1, right? Okay. Further, we can also see that this negative charge, right, this electron density will rearrange itself. That is the this arrangement of 2 bond orders 2, 2, 1 can rearrange itself within the molecule, and you can have 3 different structures based on that, right? Not kind of structures, you can have basically 3 different arrangements based on that. And now if the question is asking is that what is the average bond order between chlorine and oxygen atoms, we can just sum the individual bond orders, that is 2 plus 2 plus 1, and divide it by 3, which should give us the answer as 5 by 3 or 1.66 reckoning. But since the question over here is an integer one, our answer over here is limited to 2 decimal values, and with that we'll say that the answer over here is indeed coming out to be 1.67, and with that we'll conclude this question. Alright, this question is asking us the number of chiral carbons in chloramphenicol, right? Okay, cool. So the point over here is, right, this question is one of those not light questions over there, which are quite factual. And factual to the degree that if you don't know the factual information over there, that is basically what the structure of the compound in this question, you cannot proceed with the question, right? And so once you do know the structure, there's not much left to do with the question, right? So that's what I'm trying to say. So for example, we have the structure of chloramphenicol over here, and the question is asking us the number of chiral carbons in it. And now once we know the structure, it's pretty much simple, because you can look over here and you will find your first chiral carbon, and you will look over here and you will find your second chiral carbon, and you can scout the entire structure in immense detail, yeah, right? You can take your time, you can do it with patience, but you will not find another chiral carbon. So the point is, once we have the structure of the compound over here, there's not much left to do in this question, right? And we right away know that the answer for this question over here is going to be 2. Alright, now so this question over here has provided us a reaction, right? So what do we have? We have A, okay, liquid going to essentially what? To be gaseous, right? Okay, cool. Now what do we have over here? Let's see. The change in internal energy has been provided. Okay, fine. The change in entropy has been provided. Okay, the temperature has been provided, and delta G in kilocalorie has been asked. Okay, cool. So the point over here is, right, essentially if we are trying to find out the value of delta G, we know that this formula is one of the most frequently used ones, right? Okay. Now in this formula over here, if you look at it, right, you basically realize that you have the value of T, you have the value of delta S. What you do not have is delta H. But then again, another formula comes to our mind, which is basically this formula over here, that delta U is essentially what? Equals to delta H. Then what do we have? We had basically what? We had minus P delta V over here, which we can essentially write as minus delta NG RT over here, right? Okay, cool. So what can we further say about this? We can say that delta U plus delta NGRD over here can essentially, collectively be called as delta H, right? Okay. Now, when we put this expression in this one over here, right, we can basically, move on further, continue with the calculation of delta G. So let's just do that. So what do we get? Let's carry on everything over here, right? So what do we have? We have delta G coming out to be equals to delta U plus delta NG RD, right, minus T delta S, right? So this is what we have. Now, what are the values over here? The value of delta U has been provided in the question as essentially 2.1 kilocalorie. Okay, so this is what we have over here. And if we talk about the delta NG part, what do we have? We have 2 over here. Then remember, right, when we are talking about calories over there, right, the gas constant over here has to be taken as 2 and not 0.0821 or 8.314, because those values are in liter atm per Kelvin per mole or joule per Kelvin per mole respectively, right? Okay, cool. And over here we have the temperature, but we are essentially, missing one more thing over here, and that value over here is that essentially 2.1 was taken as kilocalorie, and this over here is only in calories, so we will further divide this value over here by 1000, right? Okay, cool. Further, what do we have? The third expression is temperature multiplied by delta S. Now, what is the value of delta S over here? The value of delta S, then again, what? Provided as 20 calorie per Kelvin, but then again, we have to convert it into essentially what? Kilocalorie, and this is what we get. Now, if you solve this value out, this over here comes out to be 2.1. Then what do we have over here? Let's do some cancellations. So if we do those, what do we get? We get this cancellation, right? Okay. So over here, what do we get? We get basically what? 12 divided by 10. So we get 1.2 over here. Further, if we do some cancellations over here, we get basically what? This over here. And essentially we can write minus 6 over here, right? So what are we dealing with? We are dealing with essentially what? 3.3 minus 6. That is essentially the answer over here is going to be turning out to be equals to what? Minus 2.7, right? And don't remember the unit of the value, right? So it's going to be essentially what? Minus 2.7 kilocalories, and that will be the answer for this particular question. Alright, so we have gone through the entire paper. We have solved each and every individual question. Now let's talk about the difficulty of this paper, right? So in my opinion, if we compare this paper to the papers of previous years, I wouldn't say that the difficulty has changed much. In fact, barring 1 or 2 questions, right? For example, the MOT questions, the tricky ones. So barring 1 or 2 tricky questions, majority of the questions fall under the category of easy to moderate. And majority of the questions can also be solved with the knowledge of NCERT alone, provided that you have indeed brushed NCERT enough. So that was it for this session over here. You can check the description below for the link for the solution doc.
For more videos and live lectures on the JEE, click on the subscribe button now.